Welcome to video 6. This is just a quick tangent exploring curvature. If you want to get back to the tutorial, you can jump ahead to video 7. Here we're just going to look into a little bit why the flat surface and the circle surface are different than all the other surfaces we could have. And so I'll go over to a blank canvas or a new canvas here to explore this a little bit more. No need to follow along here. And even though it might be intuitive, maybe it's worth mentioning why these curves are different, why the circle and the flat surfaces are different than all other surfaces. Let's just look at their bottom curves. A straight line and a circle. These are actually just very special cases, and that's why it's so easy to divide them up into segments that are equal length. The curvature at every point on these curves is the same. And so I have 3 different curves here. And one way we can look at the curvature on these is to get an evaluate curve component. So I'll just type in evaluate curve, and I'm just going to reparameterize this. And this is asking for a parameter n, so a number, since we reparameterized it, a number between 0 and 1 that's going to show us a point on this, that's going to show us where we are on this curve. And so I'll type 0.000 less than 1, and this can be our parameter n. And we're just going from one end of the curve to the other. And the outputs here are pretty convenient. We have a tangent vector and the point where we are on that curve. So you can think of the curvature here kind of like a steering wheel. So every time you have the steering wheel in a locked position, even if it's turned a little bit to the left or the right, as long as you're not moving the steering wheel at all, you're just going to keep turning around in one complete circle if you never change how the steering wheel is facing. If you have the steering wheel completely straight, then you'll just go straight forever. But if there's even a tiny curve to it, then you'll curve all the way back, eventually meeting yourself in most cases. Actually, I shouldn't say most cases, just most cases that would probably come to mind immediately. But we'll come back to that. But let's look at the tangent curves. These will be important in a lot of different cases when you're working in Grasshopper tangents. And so this is basically just what direction is the curve going at any point. So let's get a vector display component, or I'm going to get a vector display component, and the anchor is going to be the point that we're at, and the vector we want to see is this tangent. I'm actually going to increase the size of it a little bit so we can see it better. So I'll get an amplitude, and this takes in a vector and a factor to change the length of a vector, which is just a number. So we'll go between 1.000 and 5. So let's increase this size. Actually, let's go to 10. And so you can see this is basically just showing us what direction we're going in. And you can see on the circle, we're changing direction at a constant rate. And to test this, let's get a series component. And I'm actually just going to get a range. And this is asking for a domain. So the default is from 0 to 1. And then how many steps do we want between 0 and 1? And so I'll get a number between 10 and 500. So this is going to give me 10 numbers, or actually 11 different numbers, with the first and last being 0 and 1, and equal spacing between those numbers. So I don't need this series, which we're just going to use a range. And these can be our parameters. And so now we can see all of the different tangent vectors and how they're changing the same amount between any 2 points on this circle. And we can measure this. Let's get a list item component. And if I zoom in here, I can take out 2 numbers instead of just 1, or 2 outputs. So a list item will take in a list. We're going to put our vectors in there. And then it's going to ask for an index. So I'll go between 0 and 20. It doesn't really matter. We're just getting any one of these and then the one that's right after it. And so if we start at 0, then we're grabbing this vector coming out of this point, and that vector will come out of I, and then coming out of I plus 1 is going to be the next point in that list. So now we have 2 vectors coming out. Let's get an angle between those. I just typed in angle, and if I hover over this, it says compute the angle between 2 vectors. This will be the angle between those 2 vectors. and let's get a panel to see what comes out. 0.146. And if I change the input here, or the index here, let's copy this. I'm going to hide these vectors now just so we can see two at a time. And so now we're just grabbing two vectors at a time, and the angle between them is always the same. But if we go back to this curve that I referenced in, and we see how this number changes as we move to different points on the curve. So at different points on the curve is changing at different degrees. So you can see in our case, the only two cases we have in which the rate of change of the tangent is the same everywhere is the straight surface and the circular surface. There are other cases in curves. We can look at this one, for example. A spiral, the rate of change is the same at all points on the curve. But of course, we wouldn't have a surface that has a bottom curve as a spiral. Not for this project we're doing. One of the rules we made to simplify things a little bit is that the bottom curve has to be flat. It has to lie all on the same plane. But in this case, if we plug in the spiral, this is actually a reference spiral. I'm going to increase this number a little bit. And so it's not a perfect spiral, and so there will be a little bit of variation here, but not much. Let's increase this number. Anyway, we can still use our steering wheel analogy here, but this is kind of like a parking garage then. You're not changing how the wheel is turned. You have it turned a little bit, and you just hold it there, keeping it in that same spot. But since the road is going up, you're not driving along the same path over and over again. You're going up and up and up. So this refers to the torsion of the curve. How much is the curve changing away from the plane that it was on? But yeah, that's just a little tangent about tangents. And so one more tangent though before we go, a tangent off of this tangent, and we'll open another file just super quick. And I guess before that, first I'll ask the question, why are the straight line and the circle the same in this respect? And one way to answer this is just to say that a straight line is a circle with an infinite radius. So the curvature is always 0. So I'll show you quickly another way to visualize curvature. And I'll just draw a straight line and a circle and a curve that's not straight or circular. So this is a function in Rhino called curvature graph. So you can just select some curves and type curvature graph. And we don't see anything here because the hair color is white, but let's turn it to green and let's increase the scale. And we can see the circle, all the curvature is equal. The line, there's no curvature. And on this one, we can see these lines get higher when the curvature is, when it's more curvy. And then it goes to 0 right here, and then it starts curving the other direction. The curvature is basically just the inverse of the radius, 1 divided by the radius. So if we rearrange that equation, then the radius is something like 1 divided by the curvature. And for the straight line, the curvature is 0, so 1 divided by 0 points us toward infinity for our radius, which gets back to thinking about a straight line as a circle with an infinite radius. Or you can just imagine staying at the edge of a circle and increasing its radius more and more. As the radius gets bigger and bigger, this gets straighter and straighter. So for curves like this, a straight line or a circle, curves with constant curvature, when we divide them according to equal distances along the curve, those points are also equally distanced from each other in space. But that's not the case with any other curves. So in the next video, we'll come up with a strategy to get points along any curve that are equally distanced from each other in space.